So hello everyone, welcome to our seminar. Today we're happy to have Sergey Sibiryakov from Perimeter, who is going to talk about condensation and evaporation of boson stars. Please.
Thank you for the invitation, and yeah, thanks for coming to the seminar. Sorry for not being able to be in person, yeah, for various reasons. Okay, so the topic I will be talking today, okay, here's the title, and that's the work together with James Chan and Wei Xu. So what is it about? So it's about a model of dark matter, which is, I think, is simplest model of dark matter one can imagine, which is just free massive scalar field. So yeah, here it's described by Klein-Gordon equation. Well, and it happens that actually it does behave as dark matter. Well, I will discuss why. Yeah. So and moreover, we can describe it as really like we don't think of it as particles because yeah, we're thinking of it in the case when the occupation numbers are large, so that it's a coherent classical field. So that's basically the description. Yeah, and though like the model is very simple, it happens. Well, of course, I have to include here interaction with gravity. It's actually inside this formula, inside this box. And yeah, it happens that once we couple it to gravity, actually the dynamics is very complicated. Yeah, that's another funny thing that, you know, from such a simple theory, you get actually complicated dynamics, which has not been figured out. You know, like details have not been figured out yet. And what we try to do is just make a small, you know, progress in this understanding. Okay, so what we do? Okay, so first, for like dark matter, the relevant regime is non-relativistic. So there is like transition, you know, like taking non-relativistic limit corresponds when we go from real scalar field, we go to a complex scalar psi, complex wave function. Well, that's kind of standard non-relativistic limit for the fields, but yeah, just to introduce this complex function, which I will be working with. And then once we couple this thing to gravity, basically the system is described by two equations. So one is the equation this Klein-Gordon reduces to Schrödinger equation, non-relativistic Schrödinger equation. And the second equation that we have to take into account is the equation for the gravitational potential. So this phi here, capital phi, is gravitational Newtonian gravitational potential. And like the first equation is really like evolution of a wave function psi in external, you know, gravitational well or external potential, and then this potential itself is determined by the density of this, you know, this field psi. Yeah, and it's worth saying that in non-relativistic limit, the particle number will be conserved. So this the absolute psi square is literally the particle number density.
No, but in this way, you know, this you know, there is no antiparticle, right, for this field.
No, there is no antiparticle. Well, it's
right. So
antiparticle is itself. Yes. Yeah, so yeah.
Right. But then when you're saying that it is kind of kind of conserved number, it is not in the sense of, say, like Baryonic charge or whatever, because in relativistic quantum mechanics, this conservation is automatic, right? I mean,
yeah, right. Well, but we also understand why, because in principle, well, I have processes like 3 to 1, right? But I cut off this process because this one that will be produced would have energy, relativistic energy, and I don't include it. Right.
But so to the extent you neglect pairs, you know, I mean, this conservation law is kind of, I mean, it's just non-relativistic quantum mechanics, nothing else, right?
Yeah, I totally agree. Yeah. Okay, so yeah, well, examples now. What kind of particles we have in mind here? So I mean, for this dark matter. So one option is actually QCD axion. Perhaps that's the most well-motivated member of this family. And in that case, the mass, like artistic mass of the axion, is believed to be somewhere between 10 to minus 6, 10 to minus 4 electron volts. So it's a like micro electron volt range, maybe tens of micro electron volt range. Well, in principle, we should know it precisely, because the model is fixed, but we don't because the dynamics is very complicated. But yeah, it's somewhere in this ballpark. And another interesting example is so-called the fuzzy or ultralight dark matter, where the field is so light that the Broglie wavelength is comparable to the size of halos, say, astrophysical scales. Yeah, so basically its wavelength, its coherent length is so big that it's comparable to astrophysical length scales, to kiloparsecs, say, and or parsecs at least, and that can have some interesting consequences for dynamics of halos and galaxies. There have been quite a lot of interest in constraining this model. Perhaps actually it's already constrained to be beyond. So the mass perhaps is constrained to be bigger than 10 to minus 19 already. So in that case, it becomes less kind of astrophysically relevant, but still kind of all the masses in between basically are also fine. So yeah, the mass for this light dark matter could be anywhere in between 10 to minus 20-ish electron volts to 10 to minus 4 electron volts. Actually can be even a bit heavier, I think, maybe 10 to minus 2 electron volts. So we have these almost 20 orders of magnitude of the range of possible masses for this type of dark matter.
But this small mass would be okay. It would be it's not like it would be like temperature larger than this mass, or I mean, because at some point non-analytic limit stop to work, right? I mean, if mass is smaller than something.
Oh, this is not thermal dark matter, so it's never thermalized. So it's never thermalized. Yeah. It's produced.
If it's not thermalized, then it's non. Then it means that it could be relativistic as well.
No. So here there is a production mechanism where, well, for example, for this fuzzy dark matter, the idea is just that due to some random initial conditions, which we can discuss where they come from, the field happens to be away from its minimum. So yeah, somewhere away, so misalignment happens, and then and then it stays there as long as the mass is smaller than the Hubble. And that's pretty late times, and then after the Hubble, Hubble exceeds the mass, then it starts rolling down and becomes dark matter.
Right, but then the mass itself could be taken zero, right? In this case, right? Whatever at this scale, because if it's a beyond Skybell scale, then to some extent it's equivalent to. I wonder about.
Yes, that's why it stays constant. That's why the field effectively, as if it were massless, stays constant and don't move. Yeah.
Okay.
With Axion, actually, it's similar mechanism. It's also misalignment, but with a bit more like complications of dynamics.
Okay, thanks.
So Sergey, I just have a question about what's the viability of that mass range for ultralight, the fuzzy dark matter? Because I thought there were constraints on that, and maybe you'll talk about that later.
Well, not really. Okay.
I guess it's not important for you what you're going to say.
Yeah,
right?
It's not important. Yeah, first of all, it's not important. No, but I can comment on that as well. So most of them, there are various constraints. Yeah, so there are very strong constraints that rule out 10 to minus, kind of constraint 10 to minus 22. So below 10 to minus 22, that's why I didn't put these numbers. You cannot have, the fuzzy dark matter lighter than that. So 10 to minus 22, I think, is also kind of in tension with many things, which suggests that it's ruled out. Yeah. So 10 to minus 21, 10 to minus 20 is okay for most of the things, except one, which there was a kind of recent studies of dynamics. It's basically heating. So it's heating of small halos, small galaxies, not halos, but dwarf galaxies, because of inhomogeneities in this dark matter, which I will discuss. This inhomogeneous heat stars in these galaxies, and we don't see this heating of the stars, so that rules out or constrains masses, everything lighter than 10 to minus 19 electrons.
I see. Yeah, that's okay.
Right. So I think 10 to minus 19, but perhaps you should be cautious about really saying that this is completely ruled out, because that's only one observable. Like there is this kind of thing or issue with astrophysical observables that having just one measurement can suffer from systematics, or even one type of measurements. So it's good to have more like other constraints from other sources with completely different systematics. If they all accumulate, then I would say this 10 to minus 19 is kind of is the boundary.
Okay, yeah, thanks. Yeah, thanks. Thanks very much.
I also have a quick question, Sergey, about your earlier assumption on there's no number changing process because that will correspond to a relativistic particle. But you cannot forbid that process, right? Unless you turn off the self-interaction. So are you in the limit where I turn off self-interaction?
It is very small, yeah. Well, I'm assuming that there is no self-interaction, or I'm assuming that it's very small. And this is actually the case for
sure, just want to clarify about the assumption. Yeah, it's not that the non-relativistic particles wouldn't have number changing process. Really, just I assume small coupling or small self-coupling. That's the working assumption. Is that right?
Yeah, that's another assumption. No, but I think this process is also suppressed by non-relativistic. Yeah, I have to think why, but yeah, but I know that there is some regime that that have been studied where there is, I mean, it's non-relativistic, it's particle conserving, so it's still psi to the 4 kind of, yeah, it has this psi to the 4 term, but it still has U1 symmetry, so it's still particle number conserving. Yeah, I think that's, yeah, let me think what happens. Or maybe, yeah, maybe we should, yeah, if you are interested, we can come back up.
Yeah, just want to understand the assumption. Thanks. Yeah.
Okay, so yeah, so as I said, this kind of the range of possible masses, if we think of it phenomenologically, can be very wide. Yeah, and all these masses are actually described by this set of equations, and moreover, we can rescale solutions between, for different series. So basically, we can solve this system of equations once, and then just get solutions for different masses just by rescale, because this whole symmetry, this whole theory enjoys a symmetry, scaling symmetry, which I present here. So we can rescale time, space, coordinates, and the wave function itself with 3 different parameters, and then also like the mass in the Schrödinger-Boson equation and the gravitational coupling will change. And yeah, then there are different possibilities. One is when we do such a rescaling where the mass is fixed and the G is fixed. So which means that we kind of we're staying in the same theory, but we still there is one parameter freedom, and that means that we're rescaling different solutions of the same theory.
But Sergey, it is at the level when you kind of neglecting derivatives. Say, for example, for a conformal scalar field, you need, say, term R curvature multiplied, term with the curvature. So you are not neglecting all derivatives of gravitational field, right? In this way.
I'm a non-relativistic limit, so okay.
Yeah, right. But
I have in Boson, I do, but no more than that.
Right, but then at the level when you are including gravity, then you are still limit yourself by potential, right? Not including the curvature.
Right, but that's non-relativistic limit. It's not that I'm limiting. I'm just taking non-relativistic.
Yeah,
no,
okay. Okay, of course, non-relativistic limit. So it's a small momenta transfer. I agree.
Yeah. Okay, so another option is when G is fixed, but I rescale I do such a rescaling that mass changes, and that's what I said. In this way, I can relate, like solutions for different masses. So, for example, yeah, I can just solve the system once, and I will get results for QCD axion and for fuzzy dark matter in one go. So, yeah, that's a nice property. So the result, so whatever I will be talking about actually applies both to QCD axion and to fuzzy dark matter and to anything axion-like in between. So yeah, and finally, yeah, of course we can do rescaling where we change both G and M, and that's, yeah, physics. I don't know what the physics behind, but that's very handy when we do numerical calculations. Just, yeah, choice of units if you want, we can perform, and again it's nice because we can rescale different solutions. I would say get different solutions just by rescaling. Okay, so let me move. Now this system though yeah, it looks very simple, but already some, as I said, it has very complicated dynamics. And one complication, or complication, interesting thing which comes about is existence of solitons, solitonic solution in this theory, which are called, yeah, in the literature, sometimes they are called Boson stars. So what is that? This is just self-gravitating bound state of this field. Yeah, so I put certain number of particles. Yeah, and I ask what is the ground state in this sector with given number of particles, and because they have self-attractions, they will be self-attracting to each other. So that's something which is you know, like bound. They become bound, but they cannot fall completely on top of each other because of quantum pressure. I mean, sometimes people say it's quantum pressure.
No,
right?
but Sergey, but you are implying then that there is no nonlinear interaction. So it's soliton based on gravity only.
Only gravity, yes.
I see, but say I don't know, if you have a say limit of weak gravity, right? Then a soliton would be very huge by size, right?
Yeah, we're gonna see it. Yes.
I see.
So.
But, and why you call it soliton? You can say that it is planetary system. Or
I like boson star. I like boson star. So,
I see.
but some people call it soliton. Yes. Well, it is soliton actually. It is nonlinear solution of this equation. So yeah, so it's soliton in proper mathematical sense as well. But big one, yeah. So. Okay, so what I said, I mean, we can use this scaling basically. Yeah, the soliton solution. We don't need to find it for any, like for every particle number. We can just find it for some particle number and then get all other solitons with other particle numbers just by rescaling using the scaling set. So in particular, we can find something which we can call standard soliton, where just the amplitude of the field is normalized to be 1 at the center. Okay, then we can solve it. Yeah, put it's spherically symmetric, so we just put you know the spherically symmetric ansatz in the equations, and find this profile, which is oops, sorry, yeah, I think we have this pointer. Yeah, so we have this profile that exponentially decreases, you know, at large radii, and this is something localized in the center as expected. And all other solitons we can obtain, as I already said, by rescaling. So it's convenient to choose not the number of particles, but this parameter Ks, which sets the size of the soliton. In fact, 1 over Ks is just the de Broglie wavelengths of particles in the soliton, or if you want, just its width on half maximum, something like this. But then we should not forget that we should also rescale, you know, not only the width, but also the amplitude and so on. I mean, to do this scaling as you know, how to say, to do everything according to the scaling transformation that I presented before.
But look, maybe I'm missing something. When you take square of this psi, right, then it would be k to the fourth, right?
Yes.
And k to the fourth multiplied by d3x. I do not see it looks like dependent on k. No. I mean, is
number of particles. It is dependent. Yeah. That's what when you change Ks, you change the number of particles.
I see. Okay.
So yeah. So what are here? So something I already said. So this is a Ks. 1 over Ks sets the radius. Yeah, and there is even some numerical factor that we can put for you know, to be precise. So then this Es here, the frequency of the soliton. So it's a time-dependent wave function. Well, okay, it's the frequency of the soliton, but it's also the energy of particles in the soliton. So if you want chemical potential, and that scales as Ks square. So then the mass of the soliton scales as Ks. So what we see from here, that solitons which are smaller and kind of thinner, they're actually heavier.
Sergey, can I ask you this very simple naive question? So in normal nonlinear theory, where you have solitons, they have various funny properties that they can go through each other and so on. Here it's one in isolation. If I collide the two, they will shear themselves, right, due to gravity.
That's right.
So in that sense, it's only partly soliton, right?
No, I think what you are talking about, solitons you are talking about, they are in exactly solvable series.
Exactly, yeah.
No, but solitons need not be in exactly solvable series. So they have these properties, you know, what you say, that not being scattered and so on, that's because of this exact solvability of those problems. This one is not exactly solvable. So it is a soliton in mathematical sense, I think, but interaction is non-trivial.
Okay.
And that's one of the part we're addressing.
In which sense is soliton? It looks like a kind of rather like I would say a big bound state, right? Which is not like you wouldn't say that hydrogen atom is soliton, right? I mean, it's a bound state of electron and nucleon, right? Here, it looks like similar to some extent. I mean, okay, it's a more particle, but still it is kind of normal gravitational potential between them, right?
Yeah, sure. Look, well, for me, soliton, for the purpose of this name, is just to say that I have a system of equations, and I have a like nonlinear equation. I have a localized stable solution.
Yes.
So that's soliton for me. So it's a bound state, of course. Physically, it's just bound state of many particles put together.
Yeah, but even you think that it is still stable, right? So because when you said that it's not integrable system, right? It's kind of limited stability, right? Compared with the integrable system.
No, it's stable as long as it is alone. Yeah. So kind of it's there. If I kind of shake it a little bit, it will stay there. But if I put it in the environment, something will happen, and that's what I will be talking about.
Yeah, right. In the relativistic solvable theory, what was the point? Was the point that say at the level of one particle, for example, it was no pair production, no pair production, and soliton solution was in say Sam Gordon, right? You have this feature that it's all kind of elastic scattering of particle. There is a kind of time delay, but there is no real production, right? In 1+1. Here it's not the case, right?
No. Okay, I will talk more about that. So
I see.
You will see a lot of funny processes. Yeah. Okay, and here actually what Arkady already said. So the density in the center goes as ks to the 4, actually very quickly. And yeah, maybe another thing to notice from this formula is that it's also proportional to inverse. It's proportional to inverse mass of the particle itself, of the constituent particle. But I think I wanted to say that. Well, anyway, so that's the expressions. Okay, let me move. Now, yeah, what we know about the solitons, whether they are relevant to anything like any phenomenology or not. Turns out they are. So there are some results from simulations. So most of these results come just from numerical simulations, and there is very limited understanding of what's going on. So, for example, if we really like take of this scalar field as dark matter and go from initial conditions which are obtained by misalignment plus some small perturbations, the simulation set up these initial conditions and evolve the field into nonlinear halos, nonlinear structures in the universe. And what they find, they find that there are halos, actually very similar, like gross features of these halos are very similar to the ones that appear in cold dark matter simulations. So the density, like average density, follows this pattern. But there are two important differences. So one difference is that this density suffers from large inhomogeneities because of interference patterns. So if you want, like the density here is made of waves. So these halos are made of wave packets that fly around. So these wave packets interfere, and that leads to local fluctuations of density. Yeah. So and the characteristic size of this density fluctuations is the Broglie wavelengths of the particles in the halo. Okay, so 4 pi over m over some characteristic velocity, so virial velocity in the halo. But even more importantly for me, what they found, for this purpose of this talk, is that in the centers of these halos, they always see a soliton. So they see that the soliton actually form in just from featureless initial conditions and stay there. And the solitons, there is another kind of interesting relation. So they first formulated as a relation between the mass of the soliton and host halo. They saw that they are correlated. And if you look closer what the correlation is, it actually says that the size of the soliton or characteristic momentum in the soliton is of the order of the virial momentum in the halo. Or if you want, the size of the soliton is of the same order as the wavelengths. Okay, so on one hand, this property looks like at the first glance, it looks very natural. Okay, you have characteristic size, and yeah, the soliton should have characteristic size of the same kind of coherence lengths that.
Yeah, but isn't it just by definition, because you know you think of solitons classical objects, so of course it must have a.
Well, soliton can have different sizes. Yeah, so I mean, it need not have this size. Yeah, the solitons, they're maybe different from some other solitons, and that there is a family of solitons with continuous change of mass or size. But the question is why the size of the soliton should be exactly at the size of the Broglie wavelengths. Okay, on one hand, you may say, what else could it be? But on
well,
hand,
it cannot be smaller, right? It cannot be smaller, but it can be bigger, probably.
I actually will argue the opposite. You will see the results that I will have are opposite. But anyway, it's not trivial that it has this size because the density in the soliton is much bigger than the density of a wave packet. Yeah. So it's not that it's just you know, like a wave, something like a wave packet, just a bit different. No, by far no. So the density here is really like orders of magnitude bigger than the density of an average wave packet with the same wavelength. So somehow you need to condense a lot of wave packets in the same region and to get this soliton. And if you were to produce light soliton, they would be rather bigger than this one, so much bigger. So yeah, there is this. Okay, there is this fact, and actually part of my talk maybe, well, actually this whole work has been motivated by the desire to understand this correlation.
Sergey, but let's say that I will try to go to the limit where I have a less number of particles. So when KS goes, I can go to small KS, you know, in such a way that KS divided by M would be, you know, corresponding to, I mean, the total number would be not large, right? I mean, the N would be, okay. Can I go to the, no, I mean, to the limit where there are few particles or yeah, there is no connection to this?
There is no connection to that. And again, I will argue that actually that's, I mean, it's not that the process happens that first you form a big soliton, big in size, but small in mass, and then it grows in mass and becomes, it shrinks to become smaller. I will argue that no, that's not the case, and that's impossible actually.
Right, but there is no kind of one particle solution, for example. I mean, no. Let's say that I go to n, you know, small n, right? Just for no, you have, because you can change KS to make total number particle very small, right?
Yes, yes.
So at some point it would be a different physics, right, or what?
No, of course, if the particle number is really smaller than 1, yeah, I cannot describe it anymore as coherent field.
No, not smaller than 1. No, I go to 2, 1. I mean, no, kind of to have kind of like two particle bound by gravity, right? For example, no, something like this.
No, I cannot use this description. No, this description is really for large occupation numbers, and occupation numbers are large even in wave packets. So not only in soliton, but even in wave packets, they are large. Characteristic order is for this fuzzy dark matter, it's 10 to 60. Yeah, if you want.
Okay,
so that's huge. Thanks. Yeah. Okay, so what else do we know? Okay, here I basically give the facts about this solitons. So they form within the, people see that they kind of seem to form within just collapse of the halo, initial collapse, so pretty fast. So then, yeah, they obey this soliton-host color relation that relates their size to the Broglie wavelengths in the halo. So as I say, on one hand, you can think this is something natural, and even you can try to interpret it as some kind of thermal equilibrium, because there is some characteristic momentum in the soliton, and okay, you can ascribe to it some characteristic temperature, and this relation then just said that temperature of the soliton is the same as temperature of the halo. So that seems to be natural, this interpretation. Well, this suggests this interpretation, but as I will see, that actually doesn't work. So yeah. And also there is some scatter. Yeah, so the soliton-Pascal relation, okay, there is a twiddle here, so it's not precise. There is a there's a scatter. It's a kind of on average is obeyed. Well, also what happens with the solitons once they form? And here there is some controversial statements, I would say. So some papers say they don't change. Some other papers they observe some growth, which kind of some slow growth, but which then becomes even slower. So basically they grow. I mean, the mass of the soliton grows up to some point, which actually is corresponds to the soliton-Pascal relation, more or less. And then the growth becomes even slower. So the curve flatten out, and that's that's why we basically that's why other simulations don't see any growth at all, because it's so slow that they just don't see it. Because also all this is noisy. So when people measure the soliton mass from the simulations, actually the curve is not like here. It's really some noisy thing. So it's even hard to say if there is any any growth at all. On other hand, what concerns formation of the solitons and kind of more or less obeying soliton-Pascal relation, this result seems to be robust. In particular, seem not to depend very much on the initial conditions. So it also has been worked out for QCD axion simulations where the initial conditions are somewhat different, and also for some completely different conditions where people start from colliding solitons. Actually, they put several solitons on the lattice, let them fall on each other, and they don't go through each other like insoluble systems. Instead, they disrupt each other and form a halo, and also some soliton, some new soliton in the center, or maybe some remnant of one of those solitons. Hard to say. I mean, this is great. These results are great, but as usual with simulations, you cannot really go to parametrically different scales. It's very hard to reach them in simulations, and the best people can do is when the hierarchy between the size of the total size of the halo is maybe 100 times bigger than the de Broglie wavelengths. So the question is, what happens if it's bigger than that? If I crank up the mass of so imagine I do some simulations for fuzzy dark matter. So we form kind of halos that we identify with our halos, and we form some big solitons in the centers, which have sizes of kiloparsec size. But then the question, well, if I now imagine that I'm cranking up the mass of the particle, I know that in that case the Broglie wavelength shrinks, and the size of the soliton should become smaller. Well, the mass of the soliton perhaps smaller as well, but the density of the soliton actually grows. The density contrast with the surrounding actually grows, and that would mean that I'm really getting kind of delta functional object in the center if I can extrapolate these results, and that now becomes counterintuitive, at least to me. So it looks like hard to imagine that some dynamics on like megaparsec scale can create an object with size of, I don't know, less than parsec in the center of a halo and super dense. So, well, in other words, it would be good to have some analytic understanding of all these nice results to see if we can extrapolate them to various masses, or at least how much we can extrapolate them to other dark matter models. Well, actually the same dark matter model, but with different masses, with different hierarchy between the mass and the size of the halo. So any questions at this point?
Wait, I have a question. Can you hear me?
Yeah.
Okay, yeah. Wait, so what is the difference with the QCD axion initial spectrum? Is this because of the temperature dependence of the QCD potential or something? Or
no, QCD axion is more like white noise because it comes from so just short answer that QCD axion is more like white noise power spectrum, whereas this fuzzy dark matter is adiabatic or flat power spectrum. So QCD axion comes from dynamics of QCD phase transition, and then you form these different patches, kind of different Hubble patches. They have different value of the QCD axion, and overall this is people model it, or kind of it's described more or less by white noise.
Sergey, may I go a little, somewhat back and to ask, you mentioned at the very beginning that, I mean, you have the soliton, right? What prevents it from, say, diminishing its mass, say, no, like collapse of this, it could be collapse, right, of this particle, let's say temperature is 0, you know, and there's attraction, right, gravitational attraction, because what is a kind of, there is no conservation law like topological or whatever which keeps this intact or
no okay, good. So within the non-relativistic limit,
yeah,
there is Yuan symmetry, so conservation of number of particles. So
right.
this soliton is a kind of cue ball, if you want. It's kind of similar to cue ball, so it's ground state in the sector with given number of particles. Now, why it doesn't collapse to the point? Because of finite wavelengths. So this uncertainty principle does not allow it to go, you know, to go everything to the center. Sometimes people call it quantum pressure. So pressure is due to just uncertainty principle.
But it's not a quantum gravity, right?
It's not quantum. No, it's not quantum. It's not quantum gravity. It's even this pressure is not quantum. It's just the fact that it's a field. Yeah.
I see. Okay, I'm sorry, but okay.
No, thank you for asking. Yeah. So. Right. Okay. So I already said that we want to extrapolate those results. You know, just understand and extrapolate beyond the range which is probed in simulations. Yeah. Another piece of evidence that people studied is kinetic relaxation. So okay. So let me actually let's describe what they did. So I mean, they wanted to make some controlled experiment. Okay. Before I was describing cosmological simulations where you basically put something in, you get something out, but it's not very clear what happens at what stage. Yeah. So these other simulations, they say, okay, let's start with wave packets in a box. Yeah. And you can think of these like gas, axion gas in a box as inner part of a halo, for example. Then they observed what happens with distribution function in the gas. So actually first they put some Maxwellian distribution, and that's what we think is adequate, more or less adequate distribution for particles in the halo. Okay, so they put Maxwellian distribution, let's say this green, and then they see that the system wants to thermalize. Now, when system wants to thermalize, actually it wants to go away from Maxwellian, because this is a bosonic system, a bosonic gas. So it actually wants to go to Bose-Einstein distribution, or actually just to Rayleigh distribution, because it's a classical field, classical Bose field. So what is seen on the lattice, the distribution becomes more peaked. More peaked in the center. So this blue is like second step, and then like red is further on if you wait longer. So they see that the peak at small moment, at low moment, grows. And this evolution happens on a time scale which one actually can estimate. That comes from 2-to-2 scattering, but with importantly with Bose enhancement on both legs, you know, on both in states and out states. One should be cautious to include all that. So it's just gravitational scattering, 2-to-2 gravitational scattering, so the exchange of graviton. But yeah, it was enhanced, so that's appreciable. And like the most interesting part, it happens next. So when this peak grows very high, what they see next, that actually the soliton forms. So kind of this low part, these low momentum or infrared particles, they suddenly all go into soliton. And that's it. After that, the evolution basically almost stops. Okay, I will say maybe not completely, but yeah. But the main thing that there is this soliton with mass given by soliton-Hall relation. Well, or if you want, well, actually there is no halo here, but with the size given by the de Broglie wavelengths of the particles in this original Maxwellian distribution. Okay, so yeah, when I said things stop, so again, yeah, how do they measure actually the mass of the soliton? Actually, how do they understand that there is a soliton in the first place? So what is measured? So what is measured is maximal density throughout the box, And for a while, as long as this kinetic relaxation goes, actually this density doesn't almost change. Well, actually doesn't change. It fluctuates, but on average it does not change. Like from the point of view of the density, it just remains a homogeneous box. But then at some point, after this relaxation time, or further of this relaxation time, they suddenly see that the density grows. And actually we also saw it in our simulation. We also repeated the simulation and we see the same picture. So we see that the density grows, and that means that, like this big density actually corresponds to soliton. And this growth corresponds to the growth of the soliton mass as square root of time, roughly. In the beginning, I will specify later that actually that changes. But yeah, these original simulations, they basically cut, quite shortly after the relaxation time, and so that the soliton starts growing a little bit. So okay, so on one hand we get something which is kind of compatible with soliton-Hochscaler relation, that the soliton which forms has the right size. On the other hand, it continues growing, so it means that its size is actually shrinking this time. So its mass growing, but the size is shrinking. And there is no hint of any kind of thermal equilibrium or anything here. So yes, so that may be puzzling as well. So that's another piece of evidence that kind of only augments the puzzle. What did we do? So we decided to continue this line of controlled numerical experiments, but now not to start with just a Maxwellian gas, but put soliton by hand in the initial configuration. And actually that allows us to put soliton with different masses. We can put soliton which has large mass and small size, or we can put a soliton which has small mass and large size and see what happens to them. Because yeah, there must be some kind of process that is responsible for this growth. There is some kind of process responsible for the exchange of particles between soliton and gas. Yeah, and yeah, let's study this process. Okay, and also we want to keep under control the distribution in the gas, so that we don't want it really to change. And for that reason, we make our simulation short. So we kind of cut them before relaxation happens. Maybe that actually is not needed, as I will discuss later on. But yeah, at least like in the baseline simulations, we say, okay, we just simulate for time which is shorter than relaxation time, so that we can be sure the distribution of particles in the gas is Maxwellian, more or less. It remains Maxwellian and with the same parameters that we put in by hand in the beginning. What we're interested in is this growth rate. Yes, so mass, time derivative of the mass over mass itself. Yeah, that's what we are looking after. Let me make a pause here and ask if there are any questions. Or have I lost my audience? Perhaps yes.
we are all here. No.
Okay, very good. So let me go. Now the results, numerical results first. Then, if I have time, I can explain how we can actually derive analytics about that to support these numerical results. But if I don't, okay, let me at least present our numerical results. So first, we consider a soliton which is heavier than soliton-Hochscaler relation predicts. So that corresponds to Ks being larger than Kg, or Rs size of the soliton being smaller than the Broglie wavelength. So that corresponds to small, like when this parameter is small. So that corresponds to big mass, large Ks. So you can call it heavy soliton or hot soliton. So this soliton is kind of hotter than the gas. What we see that this soliton actually, yeah, let's look in here. You should look in here at this curve. We see that the soliton mass grows. Yeah, this growth is not. I mean, yeah, I think it should be visible that the mass increases slightly, I mean slowly. Yeah, the growth is slow, but yeah, it definitely grows. So it happens that heavy solitons, they actually grow, and hot solitons, though being hotter, they actually want to become even hotter. And maybe in the after thought, you can think that that's how it should be, because like solitons are self-gravitating systems, and they have negative heat capacity. So if their mass increases, they become even hotter, and kind of they want to get even more particles into them, Okay, so hot solitons grow. So light solitons. So light solitons means that this parameter, so they have now bigger size than the de Broglie wavelengths. So the mass is small. So you can call them light or cold. And they actually, their mass, and here we have this plot, we start with some mass, and actually this mass goes to zero. Well, it decreases and goes to the background. And this residual mass is actually just due to the way we are measuring the mass, we're estimating the mass. Yeah, if you want, actually we are also measuring it from the density. So it's actually what it shows here, it's not the mass of the soliton, it's just mass of the residual, it is just the residual density of the gas. So light solitons completely disappear. They evaporate. So we find that actually soliton in the gas, when it's immersed in the gas, becomes unstable. So it's either evaporates if it's too light, or if it is above, if its mass is above threshold, it grows. But there is nothing like thermodynamic equilibrium. Right here there is a comment, but okay, if you ask me, I will tell. and here there are like there's collection of our results all put together for the growth rate as a function of the mass of the soliton, if you want, or of this parameter of the size of the soliton. So this parameter is the size of the soliton. The mass of the soliton actually would be other way around. So let's say it's size of the soliton. And what are the characteristic landmarks here? So one is this curve where the virial temperature of the soliton would be equal to virial temperature of the gas. So naively, that would be the point of thermal equilibrium, but actually that turns out to be not the point of thermal equilibrium. It just happens to be unstable equilibrium. Yeah. Well, actually not equilibrium at all. Unstable equilibrium is somewhere here. So what we see next is that what I said, if the solitons are too big, too fluffy, or too light, in other words, they evaporate. And the lighter they are, the faster they evaporate. And here we have some analytical calculation that tells that this evaporation rate should grow as the size of the soliton squared. And indeed, like numerical data, they seem to follow this analytic prediction.
So Sergey, could I ask a question here? So this different behavior that you've uncovered numerically, I mean, how do I understand it from this quantum pressure that you said before, right? So is the quantum pressure growing? Is that why the soliton is growing?
No, it's not quantum pressure. It's exchange of particles. And when this evaporation corresponds to the process, actually, I also have several processes. I have a process when a particle comes in from the gas, kicks soliton, and kicks another particle from the soliton. Yeah, so it's 1 into 2 process, if you want. And another process when 2 particles from the gas collide, and one of them goes into soliton. So these 2 processes compete. And for light solitons, the first process wins. So the particles coming from the gas, they kick a particle from the soliton, and this particle goes out. For heavy soliton, the second process wins, when 2 particles collide, and one of them goes inside.
I see. So the quantum pressure never changes. Then it's always constant.
Well, kind of. It changes very slowly as a function of mass of the soliton. Yeah, well, because the mass of the soliton changes slowly, and the pressure also changes slowly. But it's not something which is important for this process,
Mm-hmm. I see.
But are these 2 processes of particle collisions? Can we really understand them perturbatively, not in terms of interaction with the soliton as a classical object, but with interaction with individual particles?
Let me flash. Yes, we can. So let me flash very quickly, then a few slides about that. But I think I really have to be quick. So yeah, so as I said, there are this process, like 2 particles, and one of them going inside, and there is also inverse process. So we have basically to write, this growth rate as a sum of 2 processes. So first one is when absorption, and second one is evaporation, evaporation process, and by parametrically, we can factor out certain, like overall scaling, but then there is a dimensionless function that we need to compute. Sorry. And yeah, we should not forget about Boson enhancement everywhere here. That's very important for everything. Okay. So then for light solitons, we really can understand it very well, perturbatively. So we just use Born approximations, and we can use Born approximation in this case for all wave function and everything. And we get, this this formula for gamma as function of its argument, so it's mu square, with coefficient, which we can also compute. So this coefficient is given by some sum of matrix elements over all excited states of the soliton. Yeah, and actually excited states are important. Yeah, that's another maybe at least interesting detail about dynamics. So when this particle comes and hits the soliton, it does not kick the particle right away out from the soliton into continuum. It actually excites the soliton. So it kicks this particle from soliton to a first excited level or second excited level, but to some excited level, which is still bounded to the soliton itself. And then other particles come in and kick out, these particles from excited levels into continuum. So there is a cascade. The particle basically goes from the ground state to excited state, other excited state, and so up, and eventually into continuum. Right. So yeah. So that's evaporation. So we do understand that really very well. That's what I said. Yeah. So bound states around soliton, they contribute about half of the result. Yeah. So it's not that the particle always goes to excited state. Sometimes it goes to continuum, but that's kind of only half of the probability. And another half, or even actually more than half, I think, comes from these excitations of various states in the soliton. And these various states, they can have different, they really change. We really see like this in the simulation, we see that these excitations at some point they become large. So the soliton really starts changing shape significantly, kind of breathing before it evaporates.
And just to clarify, so for these light solitons, their size is much bigger than the characteristic wavelengths of particles which interact with the soliton, right?
Yeah.
Okay, so then it's not surprising that you can understand in terms of scattering of individual particles. But when the size of the solitons becomes of the order of the wavelengths of the particles which scatter, then it's kind of surprising that you can still understand it in terms of scattering of individual particles, right?
No, you can still understand the scattering, but you cannot use Born approximation for the wave function. Just that. So you have to use a true wave function in the background of the soliton. Yeah, you can always understand the scattering, but technically that becomes much more complicated, and that's where I go. That's why we understand actually the heavy soliton case much less, because we have to use exact wave functions, and at least we have to use Coulomb corrections to the wave functions. That's very important. But with Coulomb corrections, we can do, and we can, we cannot compute now the factors, but we can compute the scaling. In that case, we believe that these function scales as mu to the fourth. If we just consider the process when two particles from the continuum go directly into soliton. So that part of the process, that part of the rate scales as mu to the fourth. There is caveat in this argument, because in this case, we can also imagine that there is some cascade. So particles don't go directly from the continuum to the soliton, but go through the excited states. Down the ladder of excited states. And that it's hard to take into account, because that's already not a kind of simple process. We have to solve kinetic equations that would describe how distribution through these excited states evolve. And that's why we actually don't even try to compute this number here, because this process, this cascade, will definitely contribute a lot into this number.
Sergey, but I'm kind of trying to follow. So eventually it means that the mass of soliton grows, right, in this solution, or what?
It depends where you start. Okay, let me go to, again, to these results, or summary of the results. So it depends where you start. So if you start with soliton which is too light, lighter than a threshold, given by this point, then it evaporates. There will be no soliton. If soliton starts with mass above threshold, so a bit above, then it grows. But it grows first, it grows pretty fast. This growth rate is constant. But then once it reaches actually this point, which actually corresponds to soliton-Hochschild relation, then it slows down. So the growth rate is inversely proportional to some power of mass. And simulations, they are both compatible with cube or force power. Analytics suggests more like force power. So basically, the growth rate will be going as 1 over m to the 4th. So it will continue growing, but slowly.
So it means that mass eventually diminishes or grows.
Again, depends where you start. Where do you want?
No, I mean, okay, let's say in this regime you are describing.
In here, yeah, it grows.
Okay, could it reach the level of black hole?
No, because if it reaches above certain level where self-interaction become important, that happens. Sorry, let me think. Is it self-interaction? Yeah, I think it's self-interaction. The first self-interaction becomes important, and then you will have this soliton will collapse and shed some mass out of it, but collapse not to a black hole. It will be a boson nova. So it will collapse kind of as a supernova or a boson nova, and then there will be a shock, and basically it will shed some part of its mass.
Okay, thanks.
Yeah.
So, sorry, but what if there is no? Okay, yeah, please.
Oh yeah, so your claim is if you ever start with a light enough soliton, then it'll just evaporate away. But then you said that people have these simulations where you start with nothing and then form a heavy soliton. So like, is the claim there that that the soliton just appears, like it just starts off being heavy? Like what does that look like?
Yeah,
how does it
yeah,
just go
essentially that's what happens. So my understanding for that is that, okay, actually we also did these runs. Yeah, so that's a kind of first order phase transition. So either you have a heavy soliton above certain threshold, or you don't have anything. Of course, like in reality, what happens is that what is important is this how to say is this rearrangement of the distribution function. So here we say that we immerse a soliton in Maxwellian gas, where we have a lot of fast particles, and then they would destroy the soliton. But if we wait longer for the same box, we actually see that the distribution of these particles start evolving, and we have more and more very, very slow particles, or like infrared tail grows, and then this infrared tail goes into soliton. So yeah, but once this infrared tail goes into soliton, actually, then it disappears. So the distribution after that is Maxwellian again in the gas, or more or less Maxwellian. So that's what we see. So in a sense, you know, like there is this long preparation process for formation of soliton, then soliton goes, and then everything is back, you know, like with the soliton with big mass and Maxwellian gas. Does it make sense?
Okay, but like the lead up to it is not really in a soliton state. Like when you have a bunch of these, you said you had like a bunch of like infrared particles or something, but they're just like hanging around. They're not in a soliton, and then they become a soliton.
Yeah, and these infrared particles they lead to large fluctuations of the density. Well, actually, you can see that like in the whole box, the density fluctuates like crazy. Again, somewhat similar to phase transition, and then you created this soliton. In fact, from these viewpoints of phase transitions, actually this soliton is nothing but Boson-Einstein condensate in the case of self-gravitating systems. So, or if in the systems with self-attraction, yeah. So we know about Boson-Einstein condensate in systems with repulsion, yeah. In there, okay, what happens is actually the same. If I start with some distribution function, arbitrary distribution function, it develops an infrared tail, and then this infrared tail goes into zero momentum ground state, yeah, Boson-Einstein condensate. In series with self-attraction, that cannot happen because this homogeneous condensate is unstable. Or I mean, yeah, long-range self-attraction. It doesn't happen because this homogeneous condensate is unstable. So what is the ground state? Ground state is precisely this soliton. So actually, this is nothing but Boson-Einstein condensate of of self-attracting system. So that's why there is a phase transition, perhaps. I mean, that could also tell that you either have it or you don't have it, you know, but you cannot have something in between.
But when you say ground state is big soliton, you mean that it covers the whole world, or I mean, it could be, say, a few independent solitons or whatever. I mean, when you say soliton, it means that it covers everything.
That's a good question. So in a box, in a single box, neither us nor other group, we never see more than one soliton. We see
I
just
see. So it
always
means
a
that
single
I
soliton.
see. I see. So you have
On the other hand, when you have several halos, so but the size of our box is limited. We cannot increase our size too big because then we have Jeans instability of this gas, and actually this gas goes into halo. Now, if we have well, we actually cannot have more than one halo, but other people in cosmological simulation, they have more than one halo, then they have a soliton per halo. So in a sense, every halo is a whole world where you have a single soliton. Yeah, and then there are many worlds.
I see. Okay, thanks.
Okay, well, I think I'm out of time, but actually I'm there. So let me just sketch implications. So first, first implication, there is no kinetic equilibrium actually. So this idea that this soliton-Pascal relation may somehow be explained by some kind of thermal equilibrium, no, that's ruled out. That's impossible. Then what I already said actually that this suggests this results that interpretation that formation of soliton is first order phase transition. So you either have a soliton bigger than certain threshold, determined by the temperature of the gas in the halo, in the halo or in the box, or you don't have anything. So then phenomenologically, this process may be relevant for dynamics of this kind of for the history of halo formation and solitons in these halos. So for example, this evaporation process. So if I imagine I have a big halo in fuzzy dark matter models, I have a big halo with heavy soliton and another small halo, satellite halo with a light fluffy soliton comes in this big halo. So this small soliton, light soliton will be evaporated by fast particles in the halo. So that produces a channel for destruction of solitons, of the subsolitons in the halo, which is different from what people discussed before, which was tidal disruption. Yeah, there is of course also tidal disruption of this soliton, but that's on top of that. So even if the density in this parent halo is small, still this evaporation happens. But of course, evaporation rate depends, or evaporation time depends on the local density, and actually it can be longer or shorter than the lifetime of the universe, depending on parameters. Yeah, here I give some formula. So for these parameters, it's shorter than the lifetime of the universe, but it strongly depends on everything, on density, on velocity, on virial velocity, and everything. So yeah, in principle, I don't know. It's yet to be studied how important this process is in realistic dynamics for these halos and for QCD axions, for example. Okay, that was something about growth rate, but okay, maybe I skip it. Yeah, application for soliton-Pascal relation. Basically, it says that I think, what I can say with some degree of confidence that if soliton forms, it should be bigger than what soliton-Pascal relation predicts, or bigger or equal. Yeah, so it cannot be lighter or significantly lighter than that. So it explains, it kind of explains why there is a soliton-Pascal relation, maybe from this viewpoint, that solitons that form in this collapse process, they want to be as light as they can. Yeah, because in principle, you can imagine it's harder to form a heavier soliton. Yeah, so they want to be as light as they can, and the lighter they can be is this threshold set up by evaporation. Okay, so that's why when they form, they have this soliton-Pascal mass, more or less. I think an important question is, do they form at all? Yeah, so in this simulation that people consider, they do form. Yeah, but what if I crank up the parameters? Do they continue forming, or they kind of stop forming? If there is a very large discrepancy between the parameters, too large hierarchy. We don't know. That's something to be studied. And I think here is my outlook with what to do next. And maybe just comment on the last point here. So this Maxwellization, what it means what I already said briefly, that we observe that if we start from Maxwellian distribution in the beginning, then we see that this distribution start peaking, at a low momenta. But once the soliton forms, it becomes again Maxwellian. Okay, again, what I say, in the actual simulations, all these curves are very noisy. So this is very noisy. This is very noisy. This is noisy as well. So in this sense, I cannot really say with confidence, at least with the simulation that we have at this point, I cannot say in confidence with that finite distribution, final distribution is really Maxwellian or something else. but I think it's clearly visible what we see, that this infrared peak goes away. So basically we get something which is smooth. But yeah, that still I think deserves a better, like more detailed study to understand the dynamics, because yeah, it's actually interesting that it's even surprising and unexpected. Why the soliton should maxwellize the distribution somehow? Yeah, because it's not thermal equilibrium as we discussed, and yeah, it's not clear why that happens. Yeah, I think I kind of said everything I wanted. So thank you for the attention, and I'm ready to answer more questions.
Thank you.
Thank you for the very interesting talk. I have a question that follows up on some things that people asked earlier. What is the time scale for annihilation of these axions in this context? In other words, how does it compare to everything else you told us about? If you make one of these solitons, the axions inside it can annihilate, right? Eventually. So
through their self-interaction, yeah. So the quark.
Yes. So
yeah.
How does that compare to anything?
One thing I can say, this is huge, like realistic parameters. This is, I mean, huge compared to everything.
What makes it huge? What's the parameter?
Yeah, what makes it huge? Yeah, let me think.
What is the big parameter in this problem?
Well, first of all, the self-coupling is small. Yeah, so that's.
But how small?
That's a small parameter. So.
But okay, so suppose that it's small. I mean, how does it compare to the time scale in which you're interested in studying the system on, right? I mean, I don't know.
Yeah, no, but there is some non-relativistic suppression, which I'm trying to remember why. So on top of small coupling.
Well, I'm perfectly happy to. Yeah.
Right. One thing I can say that I don't know. It's not exactly answering your question. I understand, but kind of gravitational interaction is much stronger than self-interaction. So, for example, if I were to include corrections due to self-interaction in what I did, that would be tiny. I mean, that people estimated, and basically, yeah, that smallness of the smallness of the coupling, and also the fact that gravitational interaction are long range, whereas like this quartic is local. Yeah. So okay. So there is some kind of, I mean, at least from this viewpoint.
Yeah, I'm perfectly happy to say that it's the rate is small, but the rate will depend on the density, of course, right? Because the closer that you get some stuff together, the more likely it is to annihilate. It will depend on temperature, depends on the speeds and everything like that. But whatever the rate is, since you're talking about sort of astrophysical timescales, presumably, even if it's pretty small on
no, what I'm claiming is that it's much longer than the lifetime of the universe, and really like by far longer, because some like some scales that I'm discussing here, they can also be longer than the age of the universe by by a few orders of magnitude. But this annihilation of axions, that's really by many orders of magnitude longer. So that's
is it estimated in some papers on the subject?
Yeah, that's estimated. Well, there is one review on fuzzy dark matter by Witten, Lemhui, and Tremaine, and and they discuss effects of self-interaction. Yeah, getting that this is kind of negligible for.
Okay. Thank you very much. Thank you very much. That's interesting.
So just to clarify, so your effects, is it mostly for fuzzy dark matter, or can it also apply to QCD axion?
Yes.
So both.
Yes. The same, yeah. So,
but the fuzzy dark matter would have implications for the dark matter halos, right? The dwarf galaxies, right?
Mm-hmm.
That's the difference, right?
For QCD, that implication would not be for dark matter halos, but it would be for QCD mini clusters. So these QCD
so how small are those? What are those?
Yeah, these are first kind of very dense clusters that are produced from isocurvature fluctuations of QCD axion, and typically their masses are 10 to minus 11 solar masses, something like this. Actually, they have some distribution from 10 to minus. Well, people are still discussing the distribution, and it kind of moves, from paper to paper, but it's somewhere from 10 to minus 17 perhaps up to 10 to minus 9 solar masses. So these are halos of this mass range, and the sizes are something like astronomical unit or so. No, actually, no, sorry, maybe like more like solar system size, but yeah, kind of this range. Again, depends on the mass. Well, in QCD axion, that's a picture that our big halo is actually made of these smaller subhalos, which are dense, much denser than the average density in the halos, and they have a very low intrinsic velocity dispersion.
I see.
In them.
Are these going to be seen by gravitational lensing, or?
Yes, yeah, people are kind of looking for them, or at least discussing whether it's feasible to look for them. Yeah,
I see.
Yeah, existing observations, they don't yet put constraints on that reading.
Yeah.
There have been some speculations that there are a lot of these like mini halos in ours with very sharp cusps, so with a very different density profile than the big halo that we have. So, you know, the big halo is going down like, I don't know, 1 over r squared or 1 over r cubed, whereas these go down much steeper, so 1 over r to the 1.5. How does that, would that have an effect on what you're doing?
Well, yes and no. Okay, so first of all, let me say that there is a controversy, first of all, about this power law profile in the center. And yeah, there were like early papers, they actually were suggesting even -9 to 9 quarters, like r to the power -9 quarters, so very cuspy profile. So more recent simulations, they seem to claim 1 over r, so like Navarro-Frank-White.
But this isn't for the halo. This isn't for the total halo. These are these cuspy behaviors are for these little, if you want, mini halos that were formed right away and survive, you know, outside the disk.
Yeah, but I think we're talking about the same thing. Yeah, I'm talking about mini halos now, QCD mini.
Okay.
Halo. And no, okay, and I think it's kind of still unclear what the true profile is. And the simulations that people did, they don't include, they cannot resolve boson stars. So, well, my results or their results, they suggest that there will be a boson star still. So whatever growth, whatever cusp there is, that will be cut by a boson star, because you know, like there cannot be infinite cusp because of this wave nature of this dark matter. So there will be some kind of cusp that then transitions into boson star. And the question is, what is actually the size of this boson star, which they cannot resolve from simulations. But yeah, this type of study that I'm doing, yeah, that would, or at least the Solitons-Pascal relation, that could actually tell you what size there should be.
Thanks.
Yeah. And that will affect lensing signal, because if the sky-speed profile is much better for lensing than the fluffier one, and yeah, also that like presence of this boson star can be good for lensing or bad for lensing. That a bit depends on actual size of the star. Yeah.
So regarding the cosmological history, so first there is Gibbs instability in the condensate, right, and the halos form, and then there is a phase transition in each individual halos and solitons form, right? Is this the correct picture?
Sorry, well, even the sequence of how that happens. No,
yeah.
You see, so no, not quite. So in cosmological simulation, apparently things happen at once. The Gibbs instability, which forms halos, it also is accompanied by some process that forms soliton, and that's not this slow kinetic relaxation that has been studied. Yeah, because kinetic relaxation would actually tell that it's much slower unless you push the parameters of this kind of estimate in kinetic relaxation to the boundary of the kinetic relaxation. Because, yeah, okay, one thing you can basically argue, well, actually not argue, but you know for sure that this like collapse of the halo is not a kinetic relaxation, is not in a kinetic regime, because kinetic regime requires when you have that the wavelength is much shorter than the size of the halo. And you know, in this initial collapse, they're actually of the same order first, before virialization. But apparently, the solitons form kind of before virialization or at the same moment that the thing virializes. Yeah. So.
Okay,
Yeah,
so the real
so
picture is not.
That's why
Yeah.
I mean, basically, that's still on the to-do list to understand what really happens, in this hello collapse. Yeah, that cannot be described by kinetic relaxation unless, as I say, you can kind of extrapolate the results from kinetic relaxation to the regime where the wavelength is of the same size as the size of your box. And in that case, you get that the like estimate for the formation of the soliton time agree with collapse time, with the free fall time. Yeah, more or less. So in this sense, you can say that, yeah, I mean, it's some kind of kinetic relaxation and non-equilibrium regime. So it's not really kinetic relaxation, but some kinetic process in non-equilibrium regime.
Hi, Sergey. I missed the part you discussed the relaxation time. To my understanding, you are simulating only up to the relaxation time scale. Don't care about anything afterwards. Why is that?
Well, we do that for the purposes. Yeah, let me go to this. Yeah, so we do this for well, this is our baseline simulation. So we kind of try to keep it shorter than the relaxation time to preserve, constancy of the distribution in the gas. And we still look, but what we do, we put the soliton by hand. So the soliton is already there, and then we just look how the soliton mass changes, grows or decreases. But in fact, we simulate longer. So if you want, we use just for this analysis, we use only this part of the simulation. But we do simulate longer, and we do look what happens afterwards. And yeah, depending on the initial conditions, different things happen. So for example, we also reproduced these simulations of kinetic relaxation, where you start with no soliton at all. So where you start just from the gas, with the gas, and then yeah, if we cut simulations early, we just don't see anything. So there we really have to wait until relaxation time, and actually we wait order of magnitude longer to see how the soliton which forms grows, and we find that it grows, flattens out. So it grows first is what people measured is square root of time, but then it flattens out to something which is more like time to power 1/4, which is consistent with this baseline simulation that we do, where the soliton is put by hand.
I see. Thanks. I have another naive question. Do we have any classical spin play any role in the simulation, or you ignore, you assume there's no initial spin for your system at all?
Well, solitons are spinless. Yes, so soliton is really ground state with zero. I mean, in fact, I can classify the bound states in the soliton background and soliton itself with quantum numbers, orbital momentum, and what else? Magnetic, whatever. I mean, usual quantum numbers of atomic physics. And soliton is basically S0 state. Yes, so that's zero spin. But excited states, they can have spin. And actually, we need to sum over spin to get the right answer, for this, for example, evaporation time. We sum over all spins, well, over all orbital momenta of the excited states. Yeah. So the perturbations that kind of destroy the soliton, there are monopole perturbations, but equally important are quadrupole perturbations, dipole perturbations, and so on.
But are those effects are included in your numerical simulation, or you drop them?
In the numerical simulation, they are included. Yeah, it's three-dimensional, full 3D simulation. So.
I see. Thanks.
Wait, one more question. Sorry. So this trade-off of whether like absorption or ejection dominates in like the low or high mass regime, can I think of this as mostly just coming from Boson enhancement? Like if your soliton's very light, then there are very few, like absorption's not as Boson enhanced, but if it's very heavy, absorption is more Boson enhanced, or is it more complicated than that?
It's more complicated than that, because this proportionality to the number of particles in the soliton or to the mass of the soliton, it's in both processes. Because this Boson enhanced factor, they are both for initial state and for final state. So this factor is the same. It's common for both processes. But then there is just competition between occupation numbers of the gas and the bound states. Yeah, it's more complicated.
Okay.
All right, so if there are no more questions, let's thank Sergey again. Very nice talk.
Thank you for having me.
Yeah, and see you next time.
Thanks, Sergey. Thanks, Sergey. See you.
See you. Thank you.
Bye-bye.